Hi, and welcome to Codex. Our speaker today is Deanna Needell, who is a full professor of mathematics at UCLA, the Dunn Family Endowed Chair in Data Theory, and the executive director for UCLA's Institute for Digital Research and Education. She works in mathematical signal processing, statistics, compressed sensing, and numerical linear algebra. Today, she will tell us about online non-negative matrix factorization and applications. Take it away, Deanna.
Thanks, Emily. Thanks so much for the invite and for joining. Apologies to a few of you if you just saw this talk that I gave either yesterday or last week. But I did add some new things recently, a few things, so hopefully there'll be some interesting things. And I think if you see it again, you can always ask better and more questions. So kind of the theme for the talk is how to use linear algebraic techniques for interpretability in AI. But in particular, I'm going to be talking about the online non-negative matrix factorization, which sees a lot of applications. So about 50% of this talk will be kind of introducing the method and going into a little bit of the recent theory. And then the remainder will be just a bunch of applications where I hope that you can ask questions. And if you have any ideas, comments, I would definitely love to hear them. So definitely do feel free to interrupt. The kind of conglomeration of results here is joint work with these lovely people here. Dr. Han Liu, who's a former postdoc of mine now at Wisconsin, Laura Balzano, who is at Michigan, Chris Tomer, a PhD student of mine, Wangyu Wang, a postdoc who will be leaving us this year to go to MSU, Keaton Ham, who is at Texas Arlington, and another postdoc, Kanchan Chai, who will also be leaving us. In addition to those people, a lot of the applications that I'll show were done by various student groups of mine, so my own research teams and also RU groups. And I leave it to the viewer to guess which ones are pre-2020 and which ones are post-2020. So jumping right in, non-negative matrix factorization, what is it? So I'm going to kind of give a very brief overview from the beginning, assuming that maybe there are some folks that have not seen this before. So we begin with a data matrix, and maybe for convenience, I'll say that the rows correspond to users and the columns correspond to variables. And the idea will be, as the name suggests, to factorize this matrix into two non-negative components. And those will both be very low rank. So this first component will be tall matrix, users by something like topics, which we'll discuss how to interpret topics in a second, and then topics by variables. So the first kind of thing to address is, well, why is non-negativity a big deal here? Why don't we just do something more traditional like PCA? So in NMF, because of the non-negativity, we're asking that each column of the data matrix be represented by a non-negative linear combination of the dictionary atoms that we are learning. And so in this sense, these dictionary atoms must be positive pieces of the data matrix. And so kind of this quintessential example, which is due to the seminal paper by Lian Sung, which was published in Nature quite some time ago. They took their data matrix to be images of human faces. So each column was kind of an unwound image of a human face. And if you just apply something like PCA to learn the components, you're going to get very good reconstruction from those building blocks, right? The accuracy will be quite high. But if you look at the building blocks, say if you can see my cursor down here on the bottom, all of these are just kind of nonsense to the human eye, right? They don't really mean anything to you. They don't look like part of a human face for any reason. They just happen to be the building blocks to reconstruct this data set. However, if we require non-negativity, because of this requirement, as I said, we have to sort of add these up in a positive way. And so we do actually start to see, if you stare very closely, I know this graphic is small, but it picks out things like eyes, noses, mouths, and things like this. And that has some meaning to the human looking at this. So then we're kind of learning these pieces of the face that actually make some sense. And they can still be used to reconstruct the image with quite good accuracy. Okay, so kind of going back to the schematic example, I just want to highlight kind of how one interprets these topics if they're not an image and you don't actually just see visually what they are. So because of the non-negativity, we can then just look for large values. Large values will have some sort of meaning to us. And so, for example, if I kind of scan through one of the topics, this column here, for example, and I see a large value, which I've highlighted in red, then that tells me that whatever this topic is, this user and this row has a large association with that topic. And so I can say, okay, I would like to understand what is this topic. And I go into the corresponding factor matrix over here, and I locate the corresponding row in this case, and I find this large value. And this would tell me that whatever this variable is, that variable has a high association with this topic. And so I can kind of piece together users and variables and kind of put together this puzzle. So being even more concrete, let's say if we have a data set that consists of users by movies, and the entries maybe are the ratings of those movies by the users, then I can locate a large value and I say, okay, this user has a high association with whatever this topic is. And now I go into the topic and I see maybe large values, let's say for Titanic, Love Actually, Sleepless in Seattle. These are romantic films. And so you might think that, okay, this topic is just picking up a genre, which is romantic films. And therefore this user likes romantic films. And then so you can use this to not only learn about the data, kind of learn these important features that are extracted. You can also use it for classification, prediction, lots of other machine learning tasks, but you're doing it in a way that's very interpretable, right? I understand that, okay, this person not only will like X movie and not Y movie, but they're doing that because they like this genre. So it gives you a lot more information. Okay, so mathematically, what does this look like? So many formulations, of course, as one can guess. But here we're just looking to factorize a data matrix, which I'll call X, which will be D by N, into two low-rank non-negative factors, which we'll call W and H. And we'll say W is D by R, H is R by N, where R is going to be a user chosen parameter, which will indicate the number of topics that are revealed. And then we're simply just looking for the best factors subject to the constraints of them being non-negative. And you can look for them in various norms. Frobenius norm, of course, is a natural one that works quite well. And we'll just call this W factor a dictionary matrix and H the coding matrix. The idea here is W contains those dictionary atoms, the features that explain the data, and then H contains the coding for how to explain those features back into the data set X. So I'll be, as the name suggested, looking at both the static version and the online version. So the online version of NMF considers data that is streaming in over time or sampled over time, or in some sense, a time series. And then our goal will be to learn a factorization that is best. This can mean different things. Typically will mean an expectation if we have some sort of stochastic model on how the data is streaming. And we can do many things. We can simply just learn those features again, like I kind of showed in the previous example, or we can use them for prediction. Well, we'll sort of put a window over this time series of a fixed length, and we can learn those factors and throughout those windows, and we can do reconstruction at any point in time, right? We can take W and H, multiply them together, and that gets a reconstruction X. We can use that to measure accuracy, but we can do something different as well. We can sort of slide the window beyond where we have data and look out into the future and still do reconstruction, but then that becomes sort of a prediction, right? So you're looking into the future and making a prediction. So I'll show some examples in a bit that uses this idea of this kind of simple prediction. It's a very localized prediction method. I will say that everything in this talk can be extended to tensors. It's non-trivial, as one probably is not surprised. Things get very messy in the tensor world. A lot of our linear algebra fails, but it does actually hold for these methods. So we have online non-negative tensor factorization, we have static non-negative tensor factorization, and so on, usually using something like a CP decomposition. So for the rest of today, I won't go into the tensor world. It just makes things too ugly to notate, but just wanted to note that yes, everything does actually extend. And we have follow-up papers that I can definitely point you to if you're interested.
Can I ask a question about that?
Yes, please.
Which is, what's the use case for the tensor? You already have your data, your variables, your samples. When do you need the tensor?
When your data
the
is
matrix
in tensor
can.
form, right?
Your matrix can hold any number of variables. So why would you need a tensor?
Right, so you can take any tensor data and unfold it, right, and get a matrix, but you're losing a lot of that structure. So if you have maybe a matrix that's changing over time, right, then rather than just stacking those slices across time into a matrix, you're losing a lot of that structure, right? You're losing the fact that So an entry is really the same. The pixel is the same across time. If you have a hyperspectral image, same idea, right? Yes, you can unfold into a matrix, but then you're losing a lot of that structure. So you get a lot better results actually by keeping the tensor.
Okay, thank you.
I won't go off onto that, but that's something I'm actually really interested in is, you know, when, why do you need to preserve the tensor structure? And we see in a lot of applications, it makes a lot of sense to do that. So it's worth the extra headache of not only the linear algebra, but also the practical costs. Okay, so algorithmically, to minimize this Frobenius loss, one can use something like block-form descent, and we can look at this alternating scheme where we fix W and solve for H, fix H and solve for W, and so on. So the schematic for this sort of looks like this diagram here. So we have some fixed X in the static case, and we're just iteratively fixing one factor and solving for the other, fixing that factor, solving for the other, and so on and so forth. And in the static case, the data set itself, X, is not changing over time.
Deanna, seem to have gone silent.
So this is kind of the reason why I have a lot of undergrad students. Hope I didn't lose anyone out there. A lot of undergraduates just jumping into this because A, it's easy to code, it's kind of easy to understand. You can really just run with an application and jump in right away. However, in terms of convergence, it's known that this Frobenius error is non-increasing with this multiplicative update rule, but there's no guarantee to converge to a stationary point. Okay, so that's kind of in the static case. We'll now switch to the online setting. And there's, of course, many models one can put on this. We're going to assume a stochastic model. So say that X is randomly drawn from some sample space omega according to a distribution pi. And we want to still be able to learn these best dictionary factors that describe the data in law. So here's kind of the update to the schematic. The only thing that's changing is the data set as well up here is now streaming over time. So we have X1, X2, X3, and so on. But the idea kind of remains the same. We can still iteratively and alternating update W and H. So this is the kind of exact setting we're gonna look at, and I'll show a previous result as well. We're going to consider the setting where your data X is an irreducible Markov chain. So it's streaming in a Markovian fashion on a sample space omega with unique stationary measure pi. And the goal here for this online NMF problem will be to construct a sequence of factors, W and H, W being the dictionary, H being the coding, such that almost surely we have this convergence. Okay, so what is this saying? It's just saying that the loss at time t converges to the best possible loss, best meaning over all of the possible factors, W and H, of the objective in expectation, where the expectation is taken with respect to the stochastic model on the data. Okay, so previously, this group of people here, Myril and authors, gave a solution to this problem, and they derived a rigorous proof of almost sure convergence for the empirical loss, but they did this for i.i.d. data. So independent, identically and distributed data, they were able to show the following. So the idea here will be to solve this kind of approximation problem, and I won't go into the details of how this comes. I'll just kind of point out some highlights. So we're solving, again, H and T individually, an optimization instance for each. But the trick here is we're actually going to use this surrogate function when we are solving for W. And this function is an upper bounding convex surrogate for the empirical loss. And it's given in this way here. Don't need to stare at this too much. Kind of the takeaway is that we're recycling the previous found coding factors, H1 and so forth, and we're using them as approximate solutions of the subproblem. So this allows us to only need a single optimization instance to solve for W, which of course makes things much more feasible in practice. However, you might ask, well, do I really need to store the history, all of the data, x1 through xt, as well as those learned factors, h1 through hg? That would be very problematic, especially when we're talking about large scale problems. But the good news is it turns out you don't need to. So a fairly straightforward update to the previous idea gives you this formulation here. And again, kind of the takeaway is that we introduce two aggregate matrices here, AT and BT, of very reasonable size, and they sort of capture all of the information that you need in terms of the history of the previous factors and the previous data. So the good news is you don't actually need to store the entire history, just these two matrices. And this does actually hold for the tensor case as well with a little bit of work. So here is the method, pretty feasible in practice. We kind of have these three players, the actual expected loss, the empirical loss, and then that surrogate that we were using that recycles the previous codes. So then under this scheme, this group proved for the i.i.d case with common distribution pi, that if W and H are the solutions to this algorithm here, then you get the following convergence guarantees. So you get that this empirical loss and the kind of surrogate that we're using converge to the same constant, almost surely, suggesting that indeed the surrogate is completely reasonable to use. And more importantly, we get that the gradient also converges norm to 0 almost surely. Those are the kind of convergence guarantees that we expect and would want. And it's for this, again, kind of very simple update scheme. So we were looking at this, we wanted to apply it to several different applications. My postdoc, Colin in particular, is very interested in network data and wanted to apply this to sampling networks. Of course, if you have a very large network, sampling the network independently kind of means you have to bounce around in a maybe not so easy way if the network is very large. In addition, this was early 2020, everybody was looking at COVID data. Thinking that COVID data would be independent is also quite problematic, right? We would hope at least that case numbers from one day to the next are not actually independent of each other. So there was various reasons that we really wanted to get beyond this independence assumption. And so we thought that the Markovian setting would be sort of the next step in terms of generalizing. We believe that, okay, it's not exactly true in things like COVID data and so on, but it definitely seems more reasonable to assume that case numbers are Markovian rather than independent, and sampling a network allows you to just do something like a random walk, which is much more feasible in practice. So that was sort of our goal, was to, we're not modifying the algorithm at all, so the algorithm stays exactly the same. We just wanted to extend the theory. And as you can guess, once you drop independence, things get challenging because everything breaks. But we were able to actually prove pretty much the same guarantees in the Markovian setting. So here now we have, again, an irreducible Markov chain on this finite state space with unique stationary distribution pi, and W and H are the solutions to this above algorithm time t. And we get the similar guarantees. So we get that the expected empirical loss and the expected surrogate loss converge to the same thing. We also get almost sure convergence for those two functions to the same constant. And again, we get that the gradient vanishes. Any questions here before I switch over to a different type of factorization? Okay, then I just wanted to briefly talk a little bit about CUR decompositions. This is more recent work with Longzhu Wang, who I had on that first slide. And we were kind of looking at the CUR decomposition matrix setting and asking again, can we do something in the tensor world and is it useful? So I just wanted to remind you in the matrix case, we have a D by D matrix A. If we're building a CUR decomposition, it consists of taking columns of A, and these columns put together form a submatrix, which we'll call C. Rows of A form a submatrix, which we call R, and then the intersection of those two, the literal intersection. So in this diagram, if C is red and R is blue, then this overlap is purple. That's the submatrix Q. And then there's kind of the classical theorem that says, well, if the rank of U is the same as the rank of the full matrix, then you get indeed a CUR decomposition that looks like this. So A can be factorized as C times the pseudo-inverse of U times R. And I think this fits in the scheme of sort of interpretability, right? All of these factorizations, unlike other ones like PCA and so forth, give you some understanding of what you're looking at, right? If you understand what your data is, you have some sort of feel for what the rows and columns represent, well, then you know exactly what R and C are in this case. And there's actually been quite a few applications that we found where this would be very useful and important. So I feel like it kind of fits in the same scheme. So we wanted to ask, again, can you extend this CUR decomposition from the matrix setting to the multimodal tensor setting? So just some quick motivation, what one typically does when one wants to move from kind of the two-mode world to higher modes is just see if you can take what you know in the matrix case and kind of envision it as being something more general in the tensor setting. And it turns out it's a simple observation. Here's our CUR decomposition, insert the identity as the trick usually goes. And you can just kind of separate these out and write these as mode-wise multiplications. And this sort of suggests that maybe there is some hope to kind of build this in the tensor world. So I'm going to show two theorems which look ugly, as is always the case, unfortunately, when dealing with tensors. But if you just bear with me, I'll kind of point out the highlights, and then I'll have two drawings, which I think will really solidify actually what we're doing. So we're going to just give you a taste of kind of two different CUR formulations that we derived. One we named the Chidori CUR, thanks to Dustin, who's here, and one we named the Fiber CUR. So here we've got a tensor A, which will just for convenience say has D dimensions in each mode and rank R in each mode. Then just like we kind of did in the CUR where we extract columns and rows, we're going to extract some indices for the rows and some indices for the columns. In this case, the indices for the columns happen to be a function of those for the rows, which I'll show you again in the diagram. And then from those, we're going to build these kind of R, C, and U factors analogous to the matrix case. So R in this case will be A restricted to those indices that we selected. CI is going to be a matrix, which will be the unfolding of A restricted to some particular choice of indices, which were a function of the ones we chose originally. And then UI is sort of the restriction of those matrices even further. With this construction, you get things like that the rank of these UI matrices is the same as the rank in each mode of A. You do get a CUR decomposition, which is a mode-wise multiplication of your row tensor with these matrix factors here. You get that the rank of R is the same as A, and you can say some other things about the unfolding ranks of A. The second one, this Fiber CUR, exactly kind of the same idea. You just have a little bit more freedom here. You can pick both the rows and the columns on your own. So let me just jump to the picture. So this first picture here, we're looking at a 3-mode tensor, which I've kind of drawn as this black box. And we're going to build these factors by looking at these kind of colored subtensors here. So here, the I indices that we had shown that you're selecting by the user are just going to be intervals for ease of drawing. So these 3 intervals here. And the matrix C1 then is obtained by taking this red subtensor and unfolding it along the first mode. And C2 would be obtained by taking the green subtensor and unfolding it, and C3 taking the yellow subtensor and unfolding it. And then this dotted subtensor sort of in the center, just like in the CUR case, this one shows the boundaries of the subtensor R. And in this case, the UIs are the same as unfolding R. But this is kind of the picture here. So you build these C matrices by unfolding these kind of core subtensors, and then this truly core subtensor is your tensor R. And so this is called Chidori because thanks to Dustin pointed out that it looks similar to a game of that same name. The Fiber one gives you a bit more freedom. So here the lines correspond. We just drew C2 for ease of visualization. And the red indices within each of these fibers corresponds to the rows of U2. And here, these lines may, but do not have to, pass through this, again, kind of core subtensor R. So building these, again, I think visualizing them is not as difficult as actually writing them down, gives you those kind of same decompositions. Okay, so for the remaining 15, 20 minutes, I assume, I'll just be going through some applications. So feel free again to stop me or ask more or comment. So I like to work with a lot of different nonprofits, especially. I feel like for me, it's a win-win to help a nonprofit with a data-driven project. And then that work, because it's actually with real data, usually drives a question of furthering new mathematical questions. So the first group that I've been working with for quite some time now is LymeDisease.org. And they have launched an initiative called My Lyme Data about 6 years ago now. And it's a survey, a very large survey for a very large patient base. We have about 18,000 patients in the database now. And it asks them a wide variety of questions about Lyme disease. And all of these patients had to have been clinically diagnosed by a practicing physician. Lyme disease, if you don't know, is a vector-borne disease typically transmitted by insect bite or blood-to-blood contact. And the symptoms often mimic those of other diseases. They look like multiple sclerosis, ALS, Parkinson's, fibromyalgia. And if not treated correctly and quickly, they can often become chronic. The CDC estimates 300,000 new diagnoses each year, and research strongly suggests that this is a very large underestimate for reasons, again, of poor diagnosis. The disease is in general just poorly understood. The mechanisms of the disease are poorly understood, just kind of like long haul COVID, that mechanism of why it becomes chronic, it's not clear. It's poorly funded, it's poorly diagnosed, and it's poorly treated. And so looking at this disease, the CEO of LymeDisease.org said this is a perfect example for data-driven research. And so she jumped in, and there's been a lot of work, as data said. So I'm just going to show one very small example of what one can get using something like NMF for this type of data. So in this case, I'm just going to focus on this rightmost plot here. This was kind of our newest method. And we just extracted only the symptom question. So the patients were asked to rate their severity of symptoms for a wide variety of symptoms that appear in the disease. And then what we've done is we've just done an MF with 5 topics in this case. So I'm showing the topics as columns, and I've just ordered the question so that they appear kind of in chunks. So you can see these dark orange, bright orange values are large values. Those are the ones we're looking for in each topic. And so I've just sorted them so you can kind of see how they align up in the topics. So for example, this third topic here in the center was a topic that the physicians, when we presented this to them, got a little bit excited about, because this topic corresponds to memory loss, twitching, sleep impairment, and cognitive impairment. These ring true to the physicians of being sort of a suggestion that there's a neurologic manifestation of the disease. All of these are sort of neurologic symptoms, and they do tend to cluster together naturally, as we're seeing here. And so there's this new kind of train of thinking about Lyme and other diseases, that there's different manifestations depending on the physiology of the person, depending on the co-infections of the person, which is very common with Lyme. It's very rare that you just have Lyme disease. And so this seems to suggest that there are a group of patients that have a neurologic manifestation, which could then lead to specified treatment, kind of precision medicine type of thing for those patients, and better understanding of the disease. The other thing that the physicians really noted when we stared at this with them was that this bullseye rash question actually doesn't appear strongly associated with any of these topics. And this was kind of something that goes in line with, again, what new research is showing, which is that previously, decades ago, it was believed that the only way you had Lyme disease is if you presented with a bullseye rash. It's a rash that looks like a target. And recent evidence is actually suggesting it's more like 25 to 30% of people are presenting with a bullseye rash, which means a very large chunk of patients are not even being diagnosed correctly because the physician is looking for a rash, which is not there. And so this is something that they're really looking at hard now in the clinical studies. And this was kind of, again, just something that kind of provoked that question, which is what I view machine learning in the medical field as doing. Moving away from medical data, so lots of imaging applications. Here we're using all-in-NMF for image reconstruction, which again, I'm not promoting that the compression is really the number1 application here, but it does actually work. So if there's a reason that you want to do compression with kind of interpretable building blocks, the NMF works well. So we're We're sampling the image across patches. That's where the online piece comes in. This is just an example of the patches that are learned. So again, they kind of look like the textures and colors that are appearing in the image. And then this is the reconstruction example down here. So it does work for a sort of interpretable compression. Maybe a more interesting example in the image setting is things like detecting saliency and co-segmentation and that kind of thing. So here, that's what we're doing. We're using a semi-supervised variant of NMF, which I didn't talk about too much, but you can add, other regularizer terms, one of which could be a supervised term, where you do have class labels for your training data. And then we would like to use that to do classification. So we like to classify, for example, if the image is of a cow, a dog, a car, a bicycle. And not only does supervised NMF give you good classification results, but it actually allows you to understand why an image is classified the way that it is. So rather than just sort of a black box or neural network where you're not really understanding what's going on behind the scenes, here it's very, very transparent. So for example, what we've done here is we've highlighted the pixels that are most associated with the classification label that it is given. So for example, here, the cow is, these images are being labeled as cows because of these pixels. And not surprisingly, or I guess fortunately, these pixels do correspond to the actual animal in the scene, which is not necessarily obvious. It could be that the algorithm is learning that grass is associated with a cow, right, and is going to label that image accordingly. But it is actually corresponding with the animal. In dogs, we see, parts of the face are really important, like the nose and the eyes are really important for classifying a dog. Cars, we tend to see things like tires and headlights. And bicycles, we tend to see things like handlebars and wheels. So this kind of lends to this is kind of why I like to use NMF, because it really does give you that interpretability behind the scenes, whereas a lot of these other methods do not. So this is an example of using prediction, and here we're using COVID data. So again, we're in the online setting. We have time series, and we have 6 different time series. So we have one for each country, and we looked at confirmed death and recovered cases just because that was what was available. And this was, early in 2020. So the dictionary atoms that we learned looked like this, which don't look terribly interesting, except that you do notice that this orange curve kind of tends to be different than the rest, and that's corresponding to China, which early 2020 makes sense because their case numbers look a lot different than the rest of the world. So these are the learned dictionary items. And then again, this kind of idea of learning these factors and doing reconstruction along this sliding window, and then kind of pushing that window beyond current data, looking into the future, gives you a prediction. And so we're using this method to predict these case values. And so we have the 6 different countries shown here. What we're showing here is blue is the actual data, and red is our predicted values. And so again, this is a very kind of localized prediction, right? You're using these local patterns to make the prediction, but still we do quite well. So these kind of 5, Korea, US, Germany, Spain, and Italy, we do really well. The interesting one is the one we don't do very well in, and that's China here. So you can see we were quite off when the spike occurred. And this is, again, kind of revealing of what the algorithm is doing, right? So it sees a very large spike in the actual data, and it's going to think that's going to happen, right? Because that's a pattern that it just observed. And so we tend to predict these spikes happening again, which didn't actually happen in reality. So this kind of suggests to me, I'd like to incorporate a more global model on top of this kind of localized prediction. So for example, in COVID data, I'd like to use an SIR model and kind of combine it with this localized prediction and see if we can actually get something much smoother and much better. Here is something recently, which actually I see Paulina in the audience. So we're working on some EEG data with ONMF. And this is an example from the UC Irvine EEG alcoholism data set. So 2 classes of patients, one that exhibit alcoholism, one that does not. And they have 64 electrodes. And so that's what these 64 colors are corresponding to. And so we're just looking at the actual time series from the actual EEG data. These are the dictionary items that are learned, not a whole lot of maybe insight from looking at those. Nonetheless, we still kind of get some interesting observations. So with EEG data, you're very interested in correlations, right? You want to see how different neurons work together. And so if you just took the actual EEG data itself and looked at something like a Pearson correlation, so we have the 64 nodes are on each axis, then you get some interesting correlation patterns. So these kind of extreme colors correspond to the various correlations. And we can do the same thing with the ONMF dictionary items that we learned. And so we learned those dictionary items on the previous slide, and then we look at the correlation there. And you see kind of a very simple but similar pattern. And so one might ask, well, is this really doing some sort of denoising? Is it just looking at a very high level kind of thresholded relationship and so on? So that's something that we're looking into. What I find even more interesting is if you're looking at this EEG data, not only are you interested in the actual values, right, but you're interested in the gradients of those values. You want to see if neurons are increasing together or decreasing together. And so this case here is looking at the correlation with the gradient as well, so the gradient of the time series. And then you kind of pick up these more interesting patterns emerging. And if you do the same thing, so you use ONMF with the gradient, so it has access to the gradient as well. And you learn those dictionary items and you take correlations, you get something that looks strikingly similar. So it does seem to suggest that it's those dictionary items are containing all of the information that you need. But what I found even more interesting was if you don't actually give the gradient to ONMF, so it doesn't actually see the gradient, but you increase the number of topics. So here we increase the number of topics from the previous two, and then you learn the dictionary items and look at the correlation, you get this result, which looks, again, very similar to the previous two, despite not actually giving the algorithm any information directly about the gradient. And so it suggests that ONMF is really picking up kind of additional information that's sort of hidden in other functions of the data, which I think makes it a really powerful tool. So we're continuing this work, and we've been speaking with some of the folks at the medical school to see if we can work together to understand what's going on. Kind of one of the last ones is, again, more kind of medical side. Here we're looking at an Fmri of a mouse brain. And here we're treating the data as Tensor, so it's a video over time with colors. And we're learning atoms kind of both in space and in time. And so just one example, if this is a 2-second experiment, as you can see here, and the experimenter is applying some stimulus to the mouse and wanting to see kind of what regions of the brain are active during these various tasks. And rather than sort of having to look through the video and just by eye pick out different regions that are striking to you, NMF or NTF allows you to do that automatically. So for example, this 14th atom here, which we've kind of zoomed in here on the left, really clearly shows some areas of the brain that are very active. And so if you want to know, okay, well, what does this topic correspond to? You can then look in the time domain, and I believe it corresponded to this topic if my memory serves. And you can see, okay, at this point in time, maybe 0.8 seconds, this is the topic that really is highlighted. And so it gives you sort of an automated way of looking at kind of a higher level picture to suggest, okay, this area of the brain seems to be associated with whatever the task was happening at 0.8 seconds. And it allows you to really see that in your face rather than having to kind of comb through the raw video data. So I have a bunch of graphs here for CUR as well. I think the one that I want to show is this example. So again, this is hyperspectral data. So that suggests that Tensor is kind of the right tool to use. And we're again just doing compression here as sort of an example of what one could do. All of these various methods to the eye give you good results. If you look at something like SNR, the Chidori CUR sort of wins amongst these other methods. And in terms of speed, the fiber CUR wins, not really pushing this application too much, but you can also do things like analogous to robustness. So if anyone's familiar with robust PCA, this was from a while ago, where they were able to kind of separate noise from low rank structure. And we are able to do the same thing for CUR. And so kind of a typical example in this case is to separate foreground from background in surveillance video, other types of video. And so that's what we're doing here for various data sets. And we get, kind of good runtime, better than PCA for sure, and still get good reconstruction. So it's just kind of an example that suggests even though you're gaining some interpretability because you understand the structure of the factorization more, you need not be losing anything in terms of quality of the actual task at hand. In fact, in this case, we actually improve. Same thing for basis. So I think I will stop there and happy to take any questions, and thanks so much.
All right, if everyone could smash that reaction button.